Okay, then let's think about when you have a contact between the metals and the semiconductors. Okay, so first let's think about the case when the p-type semiconductor and metals are going to have a contact. Okay, so in this case, in most of the cases, the when you think about the vacuum level, so phi, the work function, the work function of metal and the work function of semiconductor. The semiconductor side work function is larger than the metal case. Okay. In this case, as you see, the original Fermi energy is higher for metals compared with the semiconductors. So as based on what we learned, the electrons from the metal side move towards the p-type semiconductors. And as I'd like to remind you that p-type semiconductor has acceptor levels here. So originally these acceptors are accepting electrons from the valence band to give a holes in the valence band to give a conductivity. However, if you have a contact between the metals and electrons are coming, so electrons are actually captured by the acceptor levels. Okay? So based on this information, please stop the video and to draw the ohmic contact here. Okay. So let's check the answer. So originally, the Fermi level of metal becomes lower, and then Fermi energy of the semiconductor become higher to make the new Fermi energy. Right? And then since the metals has lots of electrons, it can it does not need to change the band gradually. So for metals, you can change the Fermi level easily by compensating the electrons because there are so many electrons. But on the other hand, in the case of semiconductors, there are not so many acceptor sites to compensate the band bending. So actually the band is gradually changing, and then this one was originally here and then it's going up, and then this original band also it's gradually changing with some dips, with some thickness, and then similarly for this conduction band also gradually changing compared with original band. So this is what happened here. And on the metal side, since electrons are transferred, so the surface become positive, and then electron is accepted by the donor state. So this side, the p-type side, is accepting electrons. That's why the surface become negative. And then as the away from the interface, there are some holes around somewhere in a p-type semiconductor, since this is a semiconductor. And you can see that for this contact, if you have an electron, actually, it can easily move because there's no barrier here. So, and it's called the ohmic contact. Yeah, ohmic contact. Okay. So based on this, please think about if the N-type semiconductor is going to have a contact with metals. Okay, so please draw the contact, and this one is called a Schottky contact. So please draw how to make the band for this contact. Okay, so let's check the answer. So in the case of N-type, since there are many, not many, but the donor side. So since this electron is originally excited to the conduction band, but since this energy level, Fermi energy, is higher than the metal Fermi energy, this electron is now transferred to the metal side. And this metal side, you can easily change the new Fermi energy, but in the case of semiconductor state, you cannot easily change the Fermi level. Fermi level is lower, but you cannot change the band suddenly. So band is gradually changing, something like that. So what happened here is you can see that in the Schottky contact, the metal side Fermi level becomes higher, and then the N-type semiconductor case, there's some band, so band changing region, okay, and then away from here, the electron is somewhere around, and then at the interface, since the electron is lost from the N-type, it's the surface is charged with charged positively, and then on the metal side, it's charged with negative side. Right? So for this contact and for electron, there's some barriers for overcoming this interface. It is called a Schottky contact. Okay. So here are the contact between the metal and the metals, and semiconductor and the semiconductors, and the metal and semiconductors. Okay. So by using these kind of the junctions, meaning the contacts between the two materials, we could build solar devices. Here's one of the example for solar cells. Okay, using the PN junction. As I would like to remind you, this is a PN junction. Here, this side is N side, and then this is a P side. Okay, so it's opposite drawing from the previous one. So the N type and the P type. And as I mentioned, and then there are two types of charge carriers, charge transfer, which is diffusion. So electron is, in the case of electron, from N type to P type, and holes from P type to N type. And the other one is due to the thermal excitation. Due to thermal excitation, sometimes you could excite the electron and hole at the depletion region. And in this depletion region, electron can move towards the N type, and holes can move towards the P type. This is drift current. So one of the key points first is drift current. This drift current is induced if there's some light. This is originally very small percentage, but if you could excite this band absorption by light, actually this is a very efficient way to generate charge current, right? And then you can obtain the holes and electrons and then it is connected to the circuit, and you can obtain the photocurrent. So this is how the most easiest explanation of the solar cells. So you illuminate the light in a depletion region to generate electrons and holes, and then they are moved due to the drift current to extract these charge carriers to the outside circuit. And if this wire is disconnected like this, okay, in this case, when the light is illuminated, again the electron holes are generated, and electron move towards the N-type, holes move towards the P-type. But since these two are not connected, and the electron and the holes are somehow accumulated, and then at some moment this is balanced with the diffusion current. But anyway, you can obtain a more electron on N-type side and more holes on the P-type side, which could generate the voltage, because if you accumulate charge, it can generate the voltage, right? So you can obtain the voltage. So in these two situations, you can see that this is the short circuit condition. This is open circuit condition. Okay. So what it means is here. You can see this is the original graph of the PN junction here. So this exponential increase is the diffusion current by applying the positive bias, and then this constant current was due to the drift current, the very small, due to the thermal excitation current. When the light is illuminated, this curve actually shifted toward the downside, and then even if you don't have any bias voltage, you could see some of the current, right? So this is a situation when these two are connected by wire. So it is called a short circuit current. On the other hand, even if these two are disconnected, now here the current is zero, but you could obtain the sum of the voltage due to the charge accumulation. This voltage is called the open circuit voltage. So these two are very basic properties for the photo devices or solar cells. Okay. So with that, we are coming back here later on in the lecture, but based on the junctions of the metals and semiconductors and other junctions, I'll just introduce one of the photo devices using the PN junction. Okay.